Hey, good morning and welcome everyone to Aviation Weather Radar webinar here. We are kicking it off and we have a lot of good information for you to lay it out for you. This is a pared down version of our expanded course, either viewed on e-learning, so purchase our e-learning course online and you can get the expanded. It's about 3-hour course, or attend one of our in-person instructor-led classes. So we're going to give you a lot of information today. We are not going to cover every single thing on every slide, but we're going to try to point out the most important things to you. And you will also have the opportunity to go back and view one of these webinars online on our Garmin YouTube channel. So again, we will be going fairly quickly, but I'll be pointing out the highlights and trying to bring it to focus at the end. So my name is Paul Yeomans. I've been teaching on Garmin avionics for about the last 8 years, 3 at Garmin and 5 at a university, where I was a check instructor, training officer, adjunct professor. I got most of my radar experience in a Baron, flying between 10,000 and 20,000 feet. So primarily looking up for the weather threat. Do have some time in a King Air at the different altitudes where you do have to play with the tilt management and range management a whole lot more. So we're going to jump into the session topics today, and that is basic radar principles. We want to make sure everyone has just a platform to start with. Operating airborne weather radar is definitely different than looking at ground-based weather radar. So we're going to look at the differences between the two. So NEXRAD in the United States, if you're anywhere else, we're just going to call that ground-based weather radar. So obviously you're joined for the airborne weather radar, so we're going to focus on that and the specifics of the Garmin GWX series 70, 75, and 80, and then close it out with weather threat management and a little quiz. We have 3 examples. So taking all of the tools that you learned today and applying them to the examples at the end. The first person to get the correct answer sent in question form. So on the side of your GoToWebinar page that you're looking at right now, you should have a question, so you can send those questions in there. But at the end, whoever gets the first, sends in the correct answer first for each one of those examples will get a free e-learning course code for our expanded Airborne Weather Radar course. So like I said, this is a pared down version of our course, so we're going to limit what I want you to be able to take out of this 1-hour webinar to these 4 things. So importance of practicing in VMC conditions. Don't wait until you need it. That is one of the biggest mistakes that operators do, is that they don't turn on their radar until they need it. And so if you only turn it on when you need it, when you're in the weather, then you won't be able to differentiate between ground clutter or cities compared to cells. So having the baseline understanding of what those cities look like, or ground returns, or mountains, or whatever it may be, knowing what those look like, and then you get weather in there, now you're going to have a better chance of differentiating the two. Tilt management techniques. So we cannot just leave tilt in one location. We have to be able to adjust our tilt to be pointing it at the weather that we want to be seeing those returns on. NEXRAD and airborne radar comparison. So we get a lot of comments about how our airborne weather radar doesn't look like NEXRAD. Well, it's not supposed to, it never will. And we're going to talk about some of the differences with time, tilt, ground clutter, that sort of thing. And then radar image interpretation techniques. So if you did your tilt and range management correctly, well, now we still need to be able to interpret the image that we're seeing. So that's what I want us to be able to take out of today. If you do have questions throughout the webinar, you use the app, the GoToWebinar app, send your questions through there. I have several colleagues standing by ready to answer your questions. If you do not get your answer today, then send that email to aviationtraining.webinar@garmin.com. Or if you think of a question tomorrow after the webinar, you can still send it to the that same email address. It will be located in the top right-hand corner of most of the slides today. So in the basic radar principles, let's just cover the name of it, the term radar, radio detection and ranging. So we are sending out a radio wave in pulses and it is going out until the energy is completely dissipated. But if it does strike an object, it's going to send it back just like waves do. It's going to send that back as an echo. So we're going to be referring to that as echoes coming back, being able to receive that on the antenna and then interpret it, or sorry, display it on your screen. All right, certified beam width, and I'll also call that the published beam width. So if you look in your manual for your weather radar, then it's going to have a published beam width. So for example, a 12-inch antenna has an 8-degree beam width, and a 30-inch antenna has a 3-degree beam width. 90% of the radar's energy is going to be contained in the published beam width, but there still is 10% of that energy going outside of it. So we're going to see a good example of that here in a minute. That 10%, we're going to call that additional beam energy. So it is in the center of the screen. We see weather returns will most likely underrepresent the true intensity of the hazards. I'm actually going to scratch that out and say definitely guarantee will underrepresent the true intensity of the hazard. If I'm only getting 10% of the energy, it's not going to give me that full representation of the threat that's actually out there. All right, attenuation, the reduction or loss of radar signal energy caused by external factors, so scattering or absorption of the energy. So as it goes out and strikes rain or it strikes the ground, that energy is going to be absorbed or scattered, deflected. Or if I'm pointing the radar beam at still water, it's actually going to skip off of it, and so therefore scattering away, not being able to return a signal. So if it's attenuated. Band, we're not going to focus on this too much. Band just means the combination of wavelength and frequency, and X band is the airborne weather radar, and that is a short wavelength with a high frequency. Strategic weather avoidance and tactical weather avoidance is what we are going to be referring to today. So the two different ones there, strategic being more of the planning. So using your ground-based tools, convective outlook, TAFs, PIREPs, your internet-based radar, however you're getting that information, and then the airborne weather radar whenever you're employing long-range settings. So that's strategic. I am planning out what's out in front of me for a weather avoidance. The next is tactical weather avoidance. That's when I need real-time information. I can't use NextRad, which is going to have a delay on it, to be able to give me time-critical decision making. So this is about the 20 minutes ahead. So anything that's happening within now and the 20 minutes ahead. So typically when you have your range set to 60 to 120 miles, we want to try to avoid all those storms. So within 20 minutes, we're going to be using our airborne weather radar to try to pick through some of that. So the radar beam is very similar to a flashlight beam. So let's take a look at the difference between that published and additional beam width. So on the right-hand side of your screen, you can see the pattern of that flashlight, and in the center, this would be very similar to the published beam width. 90% of the radar's energy, or in this case, the flashlight's light, is being pointed inside that beam, or that 90% that published beam width. So for a 12-inch antenna, it's an 8-degree beam width. That's 4 degrees up and 4 degrees down, and left and right. We want to remember it's a cone, not just a V. And so I'm going to definitely get some good returns in there. Anything in this very center part, that's where I'm getting my best returns, still getting good returns. And then outside of this red, I am still getting returns, but it is guaranteed to be underrepresented because that additional beam energy is not have as much focus. All right, so with that beam, just an example in comparison with the NextRad site, we have a 28-foot antenna or larger producing a 0.93 degree beam width. So just like you would on a handheld flashlight, when you adjust the focus and it gets very small, you are focusing all of that light on one area, and then you're able to see what you're pointing at better. So with a large antenna, you can get high focus and get very good reception back on the returns. when you're talking about airborne weather radar, we can't put a 28-foot antenna on, your Baron or your King Air or your Learjet, whatever it may be. That's way too big. So with a 10-inch antenna, and 10, 12, 14, 18 are the common sizes. 10-inch antenna is a 10-degree beam width, 12 inches at 8-degree beam width, and so on down to 5 degrees for an 18-inch. So that is definitely a larger beam. And so if you are coming from having flown larger antennas than a 10, 12, or 14-inch, then you might be seeing that you're picking up a little bit more ground clutter. But as far as the principles of how to fly this radar versus any other radar is going to be very similar. All right, so the beam pattern, it's shaped more like a lobe rather than a straight V. So most of the energy is right in the center, and it continues to be less and less as you go away from the center of the beam. So we're illustrating the published or certified beam width right there in magenta. We have the additional beam energy, and then side lobes that could pick up some kind of scattered imagery very close to the antenna. All right, sensitivity. So as we send out a signal, it's going to be strongest at the antenna and weaker as it goes farther and farther away. So you have better sensitivity closer to the antenna and less sensitivity the farther it goes away. Also, it is a direct comparison to wattage. How much energy are you sending out? If I'm sending out more energy, if I have, a higher powered flashlight, I'm going to be able to more sensitive to the imagery, or sorry, more sensitive to the returns out there, be able to display it. So a ground-based radar is actually pumping out about 750,000 watts. Compared that to an airborne weather radar, about 40 watts. Precipitation reflectivity, and so this is not clouds, it is precip, and the most reflective going to be the wet stuff. So over here on the right hand side we see rain, definitely reflective, wet hail, definitely reflective. But as we start moving to the left, we see our dry snow, ice crystals, and dry hail. So this stuff is already frozen, very difficult to pick up on a weather radar, on an airborne weather radar. So dry hail is definitely a significant hazard, as it may or may not be able to be picked up on the radar. Attenuation, we've already talked about. If the signal cannot penetrate, or it gets all of the energy gets absorbed by the rain or scattered, then it's not going to be able to display because it's not getting to the other side of the storm. So on the left-hand side, we see the NEXRAD image, and on the right-hand side, we see the airborne weather radar. So we get real-time information over here, but we might end up with some areas that have shadows. Shadows are indicative of the unknown. I do not know what's back there because I am seeing these dark reds right there. I don't know if I'm 100% attenuated. I'm guessing I probably am, since I have that watch right there. That's called weather attenuated color highlight, saying it's probably a shadow. But anytime you have behind a red cell like this and there's nothing, I'm going to guess that's attenuated, and I'm going to anticipate that it's a shadow and not fly back there. All right, moving on to ground-based weather radar. So ground-based weather radar in the US, we call that NEXRAD, it's the next generation radar. We have a system of many different Doppler radar sites. Has a range of 142 miles. We've already talked about the wattage, the beam size, and width. It's an S-band, and it does a vertical scan range of 0 to 19.5. So that's one of the advantages of ground-based weather radar, and why it is definitely going to show up as different compared to your airborne. So it has that automatic scanning program, so it's taking passes through the air and then giving us a composite image. So it's gathering volumetric data and giving you where is the strongest return in that column of air. So we don't know what altitude that return is coming from. We just know it is that geographical location at a certain time. NEXRAD coverage in the US below 10,000 feet. We can see we have pretty good coverage everywhere in the United States except for more of the mountain range areas. So radar is not going to be able to penetrate through ground or mountains, so there's not going to be coverage everywhere. All right, have a no coverage, right? So if you were outside of a NextRad coverage area, or if your receiver went out. So if you were using Sirius XM and for whatever reason they were unable to give you data for that area at that exact time, it might go to that purplish or gray color. Don't worry, it's not broken. You're just not receiving NextRad data at that time. You can either turn off the display or switch your map image. And I say turn off the display of the NextRad image. Don't turn your display off. Ground-based weather radar also has the data processing and transmission times. So whether it's for FISB or for SiriusXM or Garmin Connect, NOAA's collecting that data. It has to come to the central location, and they have to process that data and put it into an aviation type picture and then distribute it. So either through FISB up to satellites with SiriusXM, all that takes time. So that it's introducing a delay of 6 to 20 minutes. So whatever age you see on your screen is actually the age plus 6 to 20 minutes. So if you were thinking it's just the age, well, now your delay and your potential threat coming upon you is a whole lot sooner. Ground-based radar is also giving a mosaic image. So it's taking the multiple radar sites across the United States or across, wherever you're flying and giving you this mosaic. So it's stitching together the different radar images that it has. Another image of that composite. We don't know the altitude that that thread is at. All right, here is a great slide on why, in fact, your display is definitely going to look different from FISB to XM to the Airborne Weather Radar. So based on the intensity level, and we're going to be referring to that as decibel values. So the decibel, it's how we measure the intensity of the return. So 30 decibels is example here. If we look at our internet-based radar, it's a dark green. That dark green for 30 decibels is actually darker than the FISB darkest green. That's from 30 to all the way to 40. And then if we take that same value and look at XM, it's actually into the yellow. So even between the different ground-based systems, the display is going to look different. If we compare that down to the green of the Airborne Weather Radar, it's even a different shade of green. But the point is that you're definitely going to look different. The trick for you is to understand what it is telling you and where is it getting the information. So ground-based is delayed. It's taking a volumetric scan. Our ground-based is our airborne-based is real-time, and you are able to get a little bit better idea of the altitudes. So some of the limitations of that ground-based, we've already said it. Not real-time, may not be at your altitude or the altitudes that you think it is. It's got the delay. And you might be outside of a NextRad coverage area. So the picture on the right-hand side is out of Switzerland, and that's using the Garmin Connect. But based on your location, you may or may not have ground-based radar available in your cockpit. All right, switching over to airborne weather radar. General attributes, so it is at X-band, as we mentioned, the common sizes. Based on the size of your aircraft, it'll either be in the nose cone or on a wing mount. So the difference is here, we're switching over from more of strategic weather avoidance to tactical weather avoidance. And we're looking at 3 controls for the pilot and 2 that we're going to focus on. So range selection, adjusting your range to be able to display different distances. And then tilt management. One of the most important things for you to learn as a radar operator is tilt management. So adjusting your tilt, our basic practice for novice or intermediate or experienced, I still do the same exact technique, is to start low. I start with my tilt low and I slowly walk the tilt up until I minimize ground clutter, either the inner, middle, or outer third based on my range and altitude. And we're going to go more in depth in that in a little while. Gain adjustment is not really for a novice or intermediate user, And really, I tend to stay away from gain adjustment altogether. What that is adjusting the display of the return that the system has got. So on the screen, I can see yellow. Well, maybe I want to know, is that yellow really close to red, or is it closer to green? Because if it's closer to green, I might be more comfortable flying into it. Now, the image on the right is all ground clutter, but the example is still the same. So I can adjust that gain to try to see how close it is to another color. But if you do use gain, please remember to turn it back to calibrated. If you are a novice or intermediate user, go ahead and just stay away from that. Leave it in calibrated. If it's red, it's red. Stay away from it. If it's yellow, correlate it with some other means before you start flying into that sort of thing. So other differences here, we need to point the radar beam toward the wet returns, and we're going to see some good imagery of that here in a little bit. So if you're a low flyer, that might be more up. If you're a high flyer, it's probably going to be more down. Pointing down does produce more clutter. I do like ground clutter though. It tells me where I'm at. I have a good datum, a starting point. So ground clutter is not a bad thing. We just have to understand it and be able to differentiate it between weather threats. All right, so managing our tilt. So some of the common issues people have are either underscanning by pointing down too far, so tilting down too low, or overscanning, tilting up too high. So that's the image that's on the left, is overscanning or tilting up too high. So we are getting some returns of some weather on there, but for the most part, we were tilting up too high to be able to correlate and make good image interpretation. On the right-hand side, we're tilting down too far, so I could see a ton of ground clutter, and I'm not going to be able to make a good assessment on whether something is a city or a cell or what. So if you are tilting down too far, you might see an image like that on the right-hand side. All right, here is an example of our 14-inch antenna, and we're going to go through starting low and tilting up. And it's a great example to see what your beam energy is doing. So the published beam width and the additional beam energy, and how you can kind of see on the screen where your beam is hitting the Earth at any given point. So we're at 24,000 feet. On the right-hand side of your screen, you should see the published beam width on the top of the screen. So top right there. So we are looking at a 6.7 degree beam width. It is striking the Earth at about 38 miles, somewhere around there, and we can see the top of the beam out there. The orange line is the overly simplified curvature of the Earth, so not taking into account any unusual terrain, but for all intents and purposes, the curvature of the Earth. All right, the additional beam energy is shown at the bottom right of your screen, so I can see it's intersecting just a little past 20 miles right there. If I come over here on the left-hand side, I can see that's where my light green starts showing up, is where that additional beam energy is. And for the published beam, where it was about 40, 35 or 40, that's where my darker colors start coming in. So notice that the additional beam energy is lighter colors. Well, it's still pointed at the ground, so that is definitely an underrepresentation. It's good information for me to know. That's probably where my additional beam energy is ending. Anything that is walking inside of my inner ground clutter line is probably a cell. At least it's something for me to keep an eye on and continue to investigate as I fly. I got that big scary purple thing out there. Could be a cell, but I'm going to keep exploring with my tilt management to go see what it is. I tilt up 1 degree, and I can see my inner ground clutter line started moving out a little bit, and I can still see the differences between my published beam energy, published beam width where it strikes the ground. Tilt up to -1. Tilt up one more to 0. Let's look at those numbers again. On the additional beam energy, it's getting close to 40 on the right-hand side, and that's where my inner ground clutter line is. I look at the published beam, and it's almost out to the end, and that's where the last of my darker colors are. Tilt up to +1, tilt up to +2, and this is probably where I want to stay, either +2 or +2.5. That is minimizing my ground clutter. So based on my altitude and the range that I have set, so 80 miles, I'm looking for ground clutter returns on the outer third of my scope, this is great setting for me. So I didn't get there just by going straight to 2. I got there by starting low and tilting up. So inner ground clutter line, anything that walks in there is going to be considered a threat, at least something for me to go investigate. Tilt up to +3 and to +4, and almost everything is off of the screen entirely. So the thing I love about this is on the bottom right hand side, I can see that the additional beam energy just lifted off the surface of the Earth at 80 miles. Well, the additional beam energy is not showing anything. That's where I was supposed to start seeing ground clutter. So nothing in there is showing a return. That tells me all of that was ground clutter. And it was Kansas City. We were coming back in, taking those images. So that bright purple thing was Kansas City, Missouri. So let's explore that storm cell. So at the top of a thunderstorm, we have that turbulence bow wave, and it is not visible on radar, but it is a potential threat. Turbulence is in its name, so you could be getting a bumpy ride, but you could be having hail being thrown out the top of the thunderstorm, not something you want to overfly. But either way, it's not something that's going to be visible on your radar. Next up, we have the minimal reflectivity. So anything above that -20 line. So higher altitudes than the -20, it's going to be minimal reflectivity. If something is -20 degrees or colder, it's going to be very, very cold and probably frozen. Therefore, it's not going to be displaying very easily on your weather radar. When you get to the altitudes between 0 Celsius and -20, you're going to start seeing some better reflectivity. It's going to have some moisture on it and be more reflective, and therefore be able to see it on your radar. Maximum reflectivity is altitudes lower than the 0 degrees. And if you have a temperature inversion, then that'll be better as well, since you're going to be above that 0 degrees. Best reflectivity is going to be when you're pointing a portion of that published beam energy at the melting level. So wherever that 0 degrees is. So for standard atmospheric freezing level and standard lapse rate, 7,500 feet. And then typical summer freezing level for our latitudes is about 14,000 feet. Can change based on a number of things going on in the world with weather. And then surface area interactions can drive those wet returns to higher altitudes. So it's not saying that you're not going to get reflectivity above that. That's just where you're going to get maximum reflectivity. Okay, when we're looking at thunderstorms, and this is trying to interpret the images that you're seeing, if you haven't identified that it is a cell and not a city or not ground returns, let's look at the left-hand side. I see a steep gradient. That means it's going from green to yellow to red in a very short time period, a very short space, really. So that tells me that stuff is moving, i.e. convective and probably thunderstorm activity. Now, don't be fooled on the back end right here where it has a slower gradient. We still want to stay away from that cell altogether. All right, on the right-hand side, I see scalloped edges and hooks or fingers. So hooks or fingers are curling, so possible tornadic activity. Either way, when stuff starts looking strange like that, unusual, then it could be a city, or it's something more dangerous like tornadic activity or very strong turbulence, things like that. All right, here in the center, we have the squall line. We've been hearing that since day one as a pilot. Don't fly through a squall line. Never try to penetrate a squall line, but some of our biggest violators are actually experienced pilots because you've never flown through one, so therefore you've never been bit by one, and you start thinking, oh, that alley right there is probably big enough for me to get through, and I can see what's on the other side. Again, never try to. They can close up fast, even if you think you know what's on the other side. Now, when we talked about tilt management, we also have to have that range management. So I might be seeing this gap right here in the center because that's where I want to be going. And I could see, oh yeah, I got this. That's no problem. 40 miles, something like that. I can get through that. But when I change my range from 60 out to 120, I have a big nasty storm in there. And if stuff starts changing on me whenever I get in there, now I'm in a bad place. So try to give yourself that 20-minute look ahead. So based on your ground speed, you would adjust that range. And that's just kind of your go-to cruise setting for range. Now, I always adjust my tilt and my range based on what I'm trying to look at. I don't just keep it in one place for the entire flight. I'm kind of constantly managing it throughout the flight. Stratus rain gives us a couple different hurdles to cross. One is that it's usually lower. So if I'm flying at a higher altitude, in this picture on the right-hand side, or both of them actually, we're taking about 28,000 feet in a King Air coming back from Flying Cloud to Olathe, Kansas. And this is mostly stratus rain, so pointing down also means I'm pointing towards the ground. So it's going to be harder to pick out lower intensity precip like stratus when I'm at a higher altitude. So if it is stratus rain and I'm at a higher altitude, then it's probably not a threat. I'm just going to fly right over it. If I am lower than that, then it's going to be a little bit easier to pick up, but it is lower intensity and you might not be picking it up as much as you would see on NextRad. And another point on the right-hand side, ground clutter suppression was on when I took this image. And so I can see that it correlated this precip here on the left-hand side, a little bit out here. That's where some of those oranges were right there, but it didn't pick up everything. Target range versus target resolution. So just like the sensitivity, the farther away you get from the antenna, the less sensitive that signal is going to be. And also the ability for the system to receive that information. So I'm starting with my antenna, a very focused area. This is not a very large area from left to right. So it's kind of the same pixels or boxes, if you will, right here that I do all the way at the end of my scope. So I'm trying to cram in information out here that might be smeared. If I'm doing a long range, it's probably going to be smeared. So the sensitivity and the ability for us to display that information, it could be two small cells, or it could be one cell that's getting separated by different pixels right there. So it's trying to fill in those boxes and it's looking as a smeared image. So we can anticipate that actually being a more round target as you get close to it. Avoiding storms, want to try to avoid those storms 20 miles on the upwind side and at least 20 miles plus the speed of the cell movement on the downwind side. It's pretty typical recommendation on everything, and Garmin's of course going to stand by that. All right, we have to take into account the curvature of the Earth. Once you get to about 80 miles, you really need to start taking it into account as far as your tilt management. Inside of 80 miles, or I should say at 80 miles with standard curvature of the Earth, you're going to have about 5,000 feet of roll off. So beyond that, it seemingly goes more exponential as far as your need to take into account the altitude change and therefore manage your tilt to try to look at long range settings. To do that, we're going to give ourselves just a little bit of math and some easy math to do it. So 1 degree of tilt equals 1,000 feet of altitude for every 10 miles. So for 100 miles, just multiply that by 10. So we got 1 degree of tilt equals 10,000 feet of altitude at 100 miles. You can do the same thing for 200 or 300 miles, and the math works pretty easy for you. So that is moving the center of the beam as well as the top of the beam and the bottom of the beam. So you can kind of forecast where you're going to start seeing ground clutter and be able to manage your tilt with just some simple math. All right, here is an example for us to be able to see it. This was a GWX-70 12-inch antenna. We start out 0 degrees of tilt, so just pointing straight out, and I have 25,000 feet of altitude, AGL. So my published beam width is going to intersect the ground at about 70 miles, and that's where I'm going to start seeing my darker ground returns, or should, right? Then I have the start of the ground clutter with my additional beam energy, and that's an approximation at about 30 miles. So the start of the ground clutter with 0 degree tilt angle. This is based on AGL altitudes with normal terrain. If you're at 30,000 feet, I'm going to assume I'm going to start seeing that ground returns at about 36 miles. For 20,000 feet AGL, about 25 miles. And about 10,000 feet AGL, it's going to be 12 miles. Of course, this could change based on, cities, mountains, water surfaces, things like that. All right, so here is an example of a few cells, and this is taking kind of a simplified view at it, but it does get the point across. I am at 30,000 feet right now, 12-inch antenna, 8 width, and I want to look over there at 200 miles. I can see, based on the curvature of the Earth, my beam has gone from 30,000 feet to adding in the curvature of the Earth, I'm all the way up to 65,500 feet. So that definitely does change quite a bit compared to that 5,000 feet at 80 miles. So my beam energy right now is going to encompass 2 of those cells, and I might be picking up some of that smaller cell at the beginning. But let's say I want to point the most of my energy at the cell and get the most return, right? Get the best image back from those cells. So I'm going to point the center of the beam down 3. It's also a great place to start. Like we mentioned earlier, I start low and then I tilt up. Your starting point will change based on your altitude and based on the, your experience in the actual cockpit. So I start low, down -3, and and it turns out I'm pointing the center of the beam at that first cell. I'm going to be able to see that return there as a darker return in the middle of my ground clutter. And now we look out to something that was potentially outside of our view because of the curvature of the Earth, and the base of it would be outside of our view. And I want to draw our attention to 2 things. One is, even though it's 280 miles away, I'm still pointing the center of the beam at that cell. Right here at about 200, 220, I see this gray. This is where the curvature of the Earth is rolling off, and I have 0 visibility. Anything in that gray area, I have 0 visibility just for simple line of sight geometry. I can't see it. So this is where your outer ground clutter line is. So inner ground clutter line, that's where your additional beam energy is starting to strike the Earth. Anything inside of that is potential threat. And then I have my outer ground clutter line, and that is where the curvature of the Earth is rolling off, and I am not going to be able to see it. I literally am not going to be able to see it. So anything beyond my outer ground clutter line is either a city, something extremely reflective, or it is a big cell like this. So here's the thunderstorm that we're seeing at 280 miles. If you see something way out there, that means it's really high. For it to be that high, that means it's a big storm. So take that into account. I want to stay away from that cell. This did correlate to be a city on the right-hand side, where the farther return did correlate to be a cell. So we have short range, mid range, and long range. And this is for range selection. We've been talking a lot about tilt management. We're going to focus just a little bit on range management. So 10 to 60 miles whenever you're looking short. This is your tactical weather avoidance. You saw something that's coming in. I need to make good decisions very quickly right now. So 10 to 60 miles on the range selection when you're at a lower altitude. Tilt up as you're at higher altitudes. You're going to be trying to tilt more down, but trying to minimize our ground clutter. For the mid-range, and this is kind of our go-to for cruise, in a 60 to 120, maybe a little farther out depending on your speed and altitude. But we want to give ourselves 20 minutes of look ahead to be able to give ourselves the best tools to make the best decisions. So 250 knots, that's going to do the math and equal about 84 miles. So I'm probably going to put it at 80. 300 knots at 100, so that works out nicely. And 350 knots, it equals 116, so just round it up to 120, and you're good to go. Again, this is a starting point for your cruise. It's not where I'm going to stay the entirety of the flight, but if it's normal operations, normal kind of flight, that's where I'm going to be putting it, unless I'm going to go investigate closer or farther away. And here is when I'm going to go investigate that long range. So maybe I don't have XM, or I don't have FSB weather coming in. I want to find out what's out there, or better yet, I'm trying to get practice so I know when I do need it, I know how to use it. So looking for long range, I've got my inner and outer ground clutter lines right there, and then I've got potential storm out there on the left. Again, for it to be that high, because it's so far away, that is either like a mountain or a cell. So it's something, neither one of them I want to fly into. All right, so for ground clutter, will change based on a number of factors. As we've already mentioned, our cruise altitude, our range setting, and tilt angle settings, we've already talked about those. Adding in your surface attributes, angle of incidence, and your beam width. And then if you have the ground clutter suppression turned on or turned off, so that it's going to change based on all of those things. So here's that same flight coming back from Flying Cloud to Olathe, Kansas. and starting low and then tilting up just to get some images of this ground clutter. This is the same flight that had that stratus rain. Starting down 2, tilting up to down 1.5. I can see my ground clutter is starting to dissipate. And down 1. And this is probably where I want to be, maybe down 1.25, 1.5. That way I've minimized my ground clutter, but so anything walking in, I can see that, and I'm not overly painting it down. Like I'm not painting too much of the ground. This is not enough for me. I'm not getting enough of the image to be able to give me a good idea. Now, because of what's going on, I can compare it to my next red. I know that there's not much out there. It was just a little stratus rain. So I know I'm still comfortable, but I'm not going to keep my tilt setting right there. Now I'm going to take my range and go from that 80 to now to the 100. So now as I'm getting out to the 100, I'm starting to get more of that curvature of the earth rolling off. And so I'm going to get that outer ground clutter line. So I have my inner and my outer ground clutter lines. These things out here on the left-hand side, those did correlate to be some cities. So that's why they're illuminating, even though they're past kind of that outer ground clutter line. Tilting up to 0.5. 0.0, we can see the ground clutter starting to dissipate more. Same image that we saw earlier with that city on the right-hand side and the cell beyond that, but looking at the inner and the outer ground clutter lines to be able to give us some good tips for what's out there. And the last thing we mentioned was ground clutter suppression, so on or off. And the one thing I want to point out to you right now is the name. Ground clutter suppression. It's not ground clutter elimination. If we tried to go for elimination, we might be taking away some of your actual weather returns. So we don't want to do that. We are going to try to suppress as much as we can while still giving you all of your weather returns. So here is ground clutter suppression off, and then a second later with ground clutter suppression on. So right here in the center, this did correlate to be a string of stratus cells. So this was all weather right there. This stuff out here on the right and left side, that was ground clutter. So it did suppress a lot, and it did clue me in to, hey, that stuff out in front of me, that was cells. And the stuff on the sides did just happen to be, some brighter spots of ground returns, such as towns and things like that. So the takeaways, it's never going to appear the same as NextRad. We do need to manage our tilt and range, and try to point our beam at the wet precip, and understanding the differences between ground returns and cells. So that was the airborne weather radar principles. Let's look at the GWX 70 and 75 and 80. So it's a solid state X-band pulse compression radar system. It does horizontal sector scanning. So if you want to limit the horizontal scan to go a little bit faster, you can. Vertical scans, we have the weather attenuated color highlight. Target alert bands, which are nice, telling us what might be beyond the actual range of the antenna that we have displayed. And then altitude compensated tilt, we'll talk a little bit about. And then we have our optional ground clutter suppression and turbulence detection. So the pulse compression, we took an old magnetron radar, which had a 6,000 watt, and we came over to the pulse compression to a 40 watt. We actually get the same sensitivity being able to be displayed. So we take short pulses, it increases that range resolution but decreases the average power. But then when we compress those pulses, now we increase the power and increase the range resolution. Extended sensitivity time constant is an algorithm that is built into the radar to be able to increase the view of an image of a return that is farther away. So we've talked about sensitivity being lost the farther away from the antenna that the signal is going. Because we know the rate of decay of the signal strength, we can then compensate for that with an algorithm to display a more accurate image when you're farther away from the antenna. Therefore, it helps to prevent the idea that the storm is growing as it comes closer to you. Antenna stabilization, most of our units are changing over to automatic standby. If yours does not go to automatic standby, then you want to, before you take off, turn your radar either into on or standby to energize the servo to prevent it from jostling around and damaging itself. that would have been published in your manuals as well. Automatic frequency shifting. So spiking can occur if you have multiple radars in the same vicinity operating on the same frequency. But don't worry if you see something like that on the left-hand side for a second. Just give it a little bit. Automatic shifting is going to occur, so we'll shift the radar's frequency to another frequency, and you just give it a pass or two, and it should take care of itself. So that horizontal scan mode, we have our different range selections. It's the most common view that we're used to. So it's scanning the entire 120 degrees, unless we limit the sector, from left to right with a single tilt. So that image on the right-hand side, just imagine you're taking that whole tilt, that whole swath of air from left to right and tilting it down 1 degree or down 2 degrees. That's the kind of three-dimensional picture that you want to try to paint in your mind as you're adjusting your tilt. Here's the horizontal scan. We've already seen it when we were talking about the attenuation, and we never want to fly into that shadow. Believe it or not, we have had professional pilots tell us that, yeah, they'd fly into that shaded area without seeing the next strat. So if you have the correlation and you know it's only stratus rain, or you see it out your window, you have actual confirmation, then I might fly through that. But this is a tight space in between those two reds, so I'm still probably going to avoid the whole thing altogether. All right, vertical scan mode can be used to estimate the tops if you are in a very close range. If you're farther range, as you can imagine, with the geometry of a 4-degree beam going up, that's pretty high. So I'm probably not going to be able to adjust estimate my altitudes when I'm looking out far away. It's also never a good idea to try to estimate the tops whenever we're trying to overfly a thunderstorm. So compare this to the horizontal scan. We are taking a single bearing and adjusting our tilt from the bottom all the way to the top. So that's like 15 degrees down, 15 degrees up for a single bearing. So 4 degrees left, 4 degrees right, depending on my antenna beam size. Here's that example. So you adjust your bearing first to highlight where you think it is either a city or a cell or whatever you're trying to look at, and then you switch over to vertical mode. That way the bearing is already set at the point that you want to investigate. So that's the tool I use when I'm trying to see, is it a city, is it a cell? Cities usually tend to have flat top. We want to verify that we do see this ground clutter. We will always see this ground clutter because we're pointing the beam down when we're on a vertical mode. Altitude compensated tilt. So this is where your beam is going to be pointed at whatever the 75% of the selected range is. So at 100 miles, it's going to be pointing the tilt at whatever is at 75 miles, because that's 75% of 100. So as you climb, your beam is going to be tilted automatically to keep it pointed at whatever was at 75% of the range selected. This is a tool that can be used during climb. But once you get to your altitude, make sure and turn it back off, all right, to keep it in your normal tilt management techniques. Weather attenuated color highlight. We have the shaded area beyond any red cell where the system thinks it might have been attenuated. So over here on the right-hand side, I can see this big cell, and I don't know if we're going to be able to see anything beyond that. Because of that dark cell and the strong returns, the system thinks, hey, maybe it did not be able to see beyond that. So it's an attenuated area. It's shaded area. It tells me it might be a shadow. Probably don't want to fly in that. Target alert bands. These are the red band at the end of the scope, telling me that there is potential threat beyond the range that I have selected right there. Weather alert, that is a actual system message that could pop up if you have a threat that is within 10 degrees of your center line. Ground mapping mode is a feature that can be used if you're trying to find your geographical location. It is operating the exact same as normal weather mode. However, it's just displaying it in different colors. So I do like this example, though. I have my inner ground clutter line, and then I have a couple geographical features that are illustrated perfectly. So we've mentioned a couple times about calm water skipping. So that was a lake that had calm water. So it looks like something's wrong with my radar or something, why is there just a gap in the ground clutter? There's not a hole in the earth there, that's water and it skipped off of it. And then I have a city at the end of it. Turbulence detection in the GWX-70 is magenta. And it does have to be associated with precipitation. It's not going to just be clear air turbulence. We can't paint clear air turbulence, but if it is associated even with light precip, then we can paint the turbulence on there or display that. Here's that ground clutter suppression that we're talking about earlier. So that is an optional feature with the GWX-70. Employs the Doppler radar techniques within 40 miles and then other averaging techniques beyond that. Here's the color scale. So the 4 colors, black, green, yellow, and red being the strongest returns that are going to be displayed, and then magenta being the turbulence. We talked just a little bit about gain settings, and that's as much as we're going to talk for the sake of this presentation. We do go a little bit more in depth on our e-learning or instructor-led courses. So with the GWX-75, it includes all the same features as the GWX-70, but then it adds a multi-core processor, advanced waveform technology, and then one of the best new features is the enhanced color palette. So we actually now switch from 4 colors to 16 colors to differentiate between less than 23 decibels all the way up to more than 54 decibel returns. A red is still the same red, right? Yellow and green, they all start at the same point, but we have 4 different ones for yellow, 4 different ones for red, and even 5 different ones for green. So this essentially eliminates the need for gain. I can tell exactly what the gradient of the decibel returns are when I'm looking at the image. The big difference I want to point out here is that turbulence is now no longer magenta with the 75, it is white. We have differentiated target alert bands. So it's still a target alert band, same thing, except now it is associated with the color of the estimated signal strength. There's the turbulence detection with the white. Very strong returns coming in. With the GWX-80, with automatic mode. That's the big advancement with the GWX-80. So we took the 75 and add automatic mode. So very similar to that ground-based radar where we talked about the 3D volumetric scanning. So doing something very similar, taking multiple scans at multiple tilts, and then giving us a composite image of that return. So essentially eliminating ground clutter and displaying only those weather targets. Predictive lightning and hail regions are on there, and then predictive wind shear is an option for the 80. Whenever we're using automatic mode, turbulence detection and ground clutter suppression are automatically activated. They kind of have to be able to use it. But that auto is the 3D volumetric scanning. The basic training piece behind that is if you're flying in the weather or trying to paint your, the cells out there, turn on auto mode and leave auto mode on. Now, I would recommend switching to manual mode for your practice. Keep your skill up on it and keep your understanding of the system. But for general operation, we just turn auto mode on and leave it on, let it do its thing. So that multi-tilt, data collection, and displaying the strongest returns in the volume of air that's ahead of you. Zero blind range. So a blind range is on most radars where at the very right out in front of the antenna, you could have an area where you're not displaying any information. It's just too close to the antenna. So we take the images that we have already received, and then as you get closer, we have an algorithm that forecasts where it would be as you get closer to it. So a digitally implied zero blind range. The predictive lightning and hail region. So lightning is showing up as the yellow X's and hail showing up as the magenta triangles. Optional wind shearing. So we have the yellow cones there with the red hashes. All right, switching over to weather threat management. And we are going to go fairly quickly through the weather threat management. Again, this is something that we cover more in depth with our e-learning course and our instructor-led course. So we have a 3-step process, and we want to develop a consistent methodology. So develop how are you going to use your radar with your tilt and range management, how are you going to adjust it in flight, but then this 3-step process here, identify potential threats, investigate those threats, and assess. So I've talked a lot about, hey, if I get something inside at my inner ground clutter line, that's something to investigate. I've already identified it. As soon as it gets inside the inner ground clutter line, that is a potential threat. I'm going to go investigate it. So other identification of those using our strategic weather avoidance practices. So developing a mental picture, using all of those ground-based things pre-flight. And then also when we're in flight, we can use the FISB, Garmin Connect, Sirius XM, Storm Scope, all of those things. Airborne weather radar at long range settings, so identifying with strategic avoidance. All right, here's a good example of interpreting our radar imagery. So we have a good image on the right-hand side. We got a couple things that look unusual. So right here I have a big red cell. What should I see beyond that? So out here, I should be seeing a shadow if that was really a red cell. I have a couple other things out here we're going to talk about. So we correlate that to our map, and I love the overlay. As soon as I get that overlay, man, the image is just so easy to interpret. That was the coast of Florida. So ground does not attenuate as you go out in distance unless you're talking about the curvature of the Earth. So beyond that immediate red cell, that's why I kept having image returns, because it was the coast of Florida. Other things to see, we have water right there. Water typically starts showing up when I have about 10 to 15 knots of wind. That's when you start getting white caps. And then these things out there in the ends, because of where I am located and I know my geographical location, that's either an island or it's a cell. It would be too strange to just have water pop up like that. So it's either an island or a cell. Those did correlate to be cells, and the one on the left-hand side I correlate with my storm scope or Sirius XM lightning, and I definitely can see that's convective activity. Developing our mental picture. I have overlays, I have short range, long range, tilted differently, using all of these tools to give me the best mental picture. Tactical weather avoidance, we have our turbulence detection, target alert bands, we have our CAS messages if there's a potential threat within 10 degrees. We have our weather attenuated color highlight, so showing the shaded areas being shadows. Don't want to fly back there. I don't want to fly anywhere near those strong cells in the center there. Still identifying the precipitation-based threats using NextRad, Wenzeloff, whatever you have on board. Don't leave anything out. It's not something you want to risk with. Overlays are great. All right, so the key points there with investigating. If you do use gain, return it back to calibrated. Adjust your tilt to minimize that ground clutter and then be able to interpret those radar returns that you're seeing. So we want to allow time to identify, investigate, and assess those weather threats. So 3 potential alternatives. We got continue, deviate, and divert. Those are always the options that we've been told. Want to have effective decision making requires the time. So we're going to talk about that 20 minutes again. Develop that consistent methodology with identifying, investigating, and assessing. So key takeaways with strategic avoidance and tactical avoidance. We don't want to let a thunderstorm come up and surprise us. And now we have our quiz. So first one to send in, where is the storm? So send in question form, where is the storm? First person to send it in accurately will get a free e-learning course code to our weather course. And we will start talking about the tools that we're using to interpret this. Now, these examples do require you to have set your range correctly and your tilt correctly. And I say correctly at the point where you can identify and interpret the images. So our tips to be able to interpret this image are going to be the inner ground clutter line, and then I have this thing over there on the left-hand side inside the inner ground clutter line. That was the precipitation. Very good for sending in those correct answers. Everything else did correlate to be ground clutter. All right, example number 2, send in where you think the precipitation is. Give you just a second to send those answers in. All right, what are our tools, our tips here? I have my inner ground clutter line. There's not really anything inside of that. And then over here on the left-hand side, I have these huge purple things over here that are looking awfully scary. And then I have something over here in the center that might be precipitation. I've got, maybe a shadow back there. But over here on the right-hand side, that is either a city with a lake behind it, or that's a cell. And that I don't see a lake on my, correlated map. So that right there is the precip. I have the shadow behind it, dead giveaway. And then in the back there, it was Iowa City and Cedar Rapids. It just happened to be that the curvature of the Earth, because we're set to 160 miles, was rolling off. Over here on the left-hand side, we have Des Moines, Ames, Fort Dodge. That was I-35. So interstate going through there with all of the cities along it. So that's why they were illuminating, and that's also why there wasn't a shadow associated with any of those strong returns. All right, example number 3, send in those correct answers. Where is the precipitation? Based on this particular range and tilt setup, I've got an inner ground clutter line, and I do have some things inside of this. They're not very strong returns, so I'm going to keep an eye on it. And then I have this this red cell, and then I have that no returns behind it. So that did turn out to be precipitation with shadow. I also had that precipitation up front. It just wasn't as much of a threat yet. Everything else did correlate to be ground clutter. All right, so that last image, I took that last image and turned ground clutter suppression on. So all of the precipitation is still there. It's still being displayed. So all of this was the precipitation, but we still had some of that ground clutter coming in. Now, based on this image, I don't have the full story because it's still showing some of those brighter returns on the sides. So I always use ground clutter suppression on and off. So the shadow actually gave me a better indicator that this was a cell than with ground clutter suppression on. So use it on, use it off. We always say train as you fly, fly as you train. That's my last pitch to you, to please use your radar in VFR conditions before you get into the weather. That way you can tell the difference. This is just some starting point tips for where you are going to start your tilt and range based on your phase of flight. So it's not where you're going to keep it. It's not even where you're going to keep it from day one, but it's a starting point. Okay, if I'm at cruise, tilt to minimize ground clutter. If I'm on approach, up about 7.5 degrees as I'm coming in, it might be closer to 5 for you, but that's where you start and then manage it. Here's a different way of showing that, but trying to match your ground clutter with what you're trying to display on your screen, understanding the differences. But we practice, practice, practice. Here is your homework. Understand how cities will appear. Understand how bodies of water will appear, calm and strong winds, mountainous terrain, flat terrain. Get to know your routine flying environment. Understanding the differences with XM and how low intensity precip depicted on there. How's it going to look? Understanding the freezing level, trying to point that at the wet returns and differentiating between the ground clutter. So the 4 things I said we should get out of this today: importance of practicing in VFC conditions. Don't wait until you need it. The tilt management, so we've learned a lot about that. The differences between NextRad and Airborne comparison, and radar image interpretation. I love that last bit with the examples because we get so many correct answers. You have proven to yourself that you have learned and that you have the ability to interpret if you manage your range and your tilt correctly. Correlate all the information that you have in a mental picture to be able to make effective decision making. If you do like this training and you want more, we do have quite a few e-learning courses. You can go to flygarmin.com/training for e-learning courses. We have instructor-led courses at our Olathe campus, at other campuses, and custom classes. So check us out. If you do have more questions after today or after this webinar is closed, please send those questions to aviationtraining.webinar@garmin.com. All right, thank you, everybody. It's been a pleasure talking with you, and fly safe.